Okay, can you hear me?
Yes, thank you.
Yeah, thank you. Hello, everyone. I'm Munetaka Otani, Senior Software Engineer at IBM Quantum. Thank you for giving me an opportunity today to introduce our software stack. So earlier this year in April, IBM started a new community together with several partners, RPI, Pascal, STFC. Within this community, we explored how users could access quantum resources through SRAM, the workload manager many HPC center already use, so that quantum workload can be run just like classical one. And we have been turning that idea into reality as an open source software. So we have been working closely not only those four partners, but also with partners like JC and other HPC partners to make sure the software is easy for multiple quantum vendors to join. At the same time, we have been listening carefully to the feedback from those people in the HPC community to make sure the stack fit naturally into existing HPC environment and their ecosystems. So everything we produce is fully open source. So you can even run the entire stack, including SLAM, on your own PC. So as of today, more than 10 organizations have joined the community, and our software stack has already been deployed in 4 data centers where it's being evaluated or used in practice. So data center, RPI, STFC, and other 2 partners data centers. So, and we don't just provide the software, so we also support the partner so that they can use it for their scientific experiments. So thanks to those collaborations, several great papers have already been published in this year. So we always take an open approach, so that we have been running the bi-weekly open call to communicate with team member. And also this means not only discussing specification, but also providing working implementation. So now I'd like to walk through the user experience of running quantum workload on the SLAM with our software. Basically, in the same way classical workload are run. Just like a classical job, user prepare the SLAM job script on the left up, and their workload program. So in the script, in addition to the user option, user need to specify the quantum computer name they want to use with the -- QPU option. So in this picture, the -- QPU IBM Feds, this is the name of the quantum backend provided by the IBM quantum platform. So in this example, the workload is the Qiskit program. So if you are familiar with Qiskit, you will notice that almost all of the code looks exactly like what you find in the Qiskit website. So the difference is that backend information called the target comes from the service called by the QRMI services. QRMI service. So detailed information regarding on the target will be provided by the QRMI and our software stack automatically based on the input of the user job script. So the program itself never directly specified any backend name in the program. So on the other hand, on the system side, system administrator create a configuration file named QRMI underscore config.json file. So this file defines the resource name, for example, the IBM Fairs, Fresnel, this is one of the service name of the Pascal Cloud. And any runtime parameter which each QRMI implementation needed. So for example, the API endpoint and some credential if the access is managed, should be managed by the system level. So the resources listed here become available for the user when they submit the job. For example, if IBM Face is available in this configuration file, user can specify this content backend in their SLAM job script. Okay, so as you can see, the user experience is almost identical to submitting classical workload. This is what we wanted to provide to the HPC community to expand the usage of the quantum resource and accelerate our quantum-centric supercomputing strategy. So this diagram gives a high-level overview of our stack. So the API library for accessing quantum backend is called as QRMI, Quantum Resource Management Interfaces. So SLAM and HPC workload called this QRMI to execute quantum workload under the SLAM. So on the left side, so this is a SLAM cluster daemons. So the SLAM cluster daemon also need to interact with quantum resources. For example, the checking the resource status or the locking and unlocking resources. So in order to call QR from the SLAM daemon, so that we built a Spank plugin that can be deployed. Can you hear me?
Yeah. Hello? Hello? Oh, yeah, I
Hello?
can hear you. Yes, I can hear you now.
Oh. Okay. Sorry. Can you hear me?
Yes. Yes.
Okay, so sorry, my microphone was troubling. Yeah, so we built a Spank plugin that can be deployed on the cluster. This is our product. So this plugin dynamically load the QRMR library and invoke some function such as lock and unlock the resources API. So QRMR also provides the API to run the quantum circuit created by the HPC workload. So the payload format is vendor specific. So the IBM uses OpenQSE 3 and the QPy, and Pascal uses the Pascal sequence, and the other vendor can use their own format. So in the current implementation, everything between the QRMI and the quantum resources uses the REST API. So now let's go a bit deeper into the actual flow. So this diagram illustrates the sequence of the code. So in the SLAM, so each job goes through the 3 phases. So the prologue, task execution, and epilogue. So the Spark plugin provides a callback for those 3 phases, which let us control the entire job life cycle. So in the prologue phase, so the environment variable defined in the QRMI config JSON and any processing defined in the additional prologue script are executed. So this set up the environment needed for the job. So for some quantum resources also require the resource locking. So and we do that here. The user job won't be delayed by things like calibration. So that before the task start, so task init called the set environment variable like job timeout. So then the quantum workload program. So in the previous example, so the Qiskit program, Python program, quantum workload program is forked and executed with those environment variable setting. And at last, when job finished, resources unlocked and the memory is released. So you can see on the right side, so the quantum resources we target include both cloud QPU and on-premise system. So they might also be the parallel pipeline as a classical computing, and it depends on the implementation. So that for some quantum service may contain the scheduler inside in the quantum resources. We targeted such kind of the backend system as a quantum resources. So now I will introduce the API to interface to those quantum resources. Yes, this is a QRMI. So this is a scene and vendor agnostic layer to access and control, monitor, and underlying on-premise and cloud bursting quantum systems. As you can see that QRMI implementation is based on the last implementation. This is performant, and also that we can utilize many of open source ecosystem. So it also provided Python binding, also the C binding to ease of integration by the user side. So as you can see that we defined the QRMI interfaces API. So not only the SLAM, but also other workload management system, also the workload management system and the workflow management system such as Prefect and other tools. Also the HPC workload, Qiskit, and other SDK program can invoke the QRMI interfaces. So QRMI consists of 3 major functional blocks. First one is that resource acquisition, so locking resources for use and unlocking resources for use. The next one is the task running, running task, quantum task from the API invocation. The last one is the accounting and the metrics functionality. So this is under the development. So we communicate with the HPC community members. So the getting accounting metrics, such kind of the QPU utilization parameter value, must be important for the by the HPC community. So this is the highest priority we are tackling, and we are going to provide functionality to retrieve the accounting information. So as of today, we have succeeded to support the IBM cloud interfaces and on-premise interfaces, in addition to the Pascal cloud and also the Pascal on-premise, for example, the simulator we supported. And we have started to discuss two more quantum vendors to add their quantum backend to support in the QRMI. So this is a major class definition, quantum resources. So I listed the function names in the table. So as you can see that this must be very similar to other quantum resource interfaces. So the line table line in the purple line is used by the SLAM plugin. Others are invoked by the HPC workload, such as the Qiskit runtime. So it's accessible to check the device is accessible, acquire and release correspond to the resource lock and unlock. Metadata, we return the JSON format that contain the number of QPU, backend name, others metadata. And others are task execution related functionality. So this QRMI library is configured via the environment variable by considering the distributed environment execution middleware. So each QRMI vendor defined each environment variable to configure their runtime parameter, like below. So as you may know from the previous slides, so that you can find the network middleware. So that I'm going to explain briefly in this part. So as you may know that SLAM is environment-driven distributed environment. So all of the configuration parameter are provided via the environment variable. So this means that if user HPC workload is a user program, so the user can know the cluster-wide credential by retrieving all environment variable from the code. For example, the get m and m belong Python API. So this must be the security issues. So we need to resolve as soon as possible. This is under the discussion and development, so that we are thinking of allocating the secured reverse proxy functionality. So each QRMI REST client will invoke the reverse proxy instead of direct communication to each endpoint. So this reverse proxy is secured and run as administrator permission. So this reverse proxy will retrieve the configuration parameter to retrieve the credential once the request comes from the QRMI. And it automatically authenticate with the IAM to get the JWT token and the other access token. And then this reverse proxy will modify the HTTP header of the REST API and transmit the modified HTTP request to the target quantum backend resources. So that we are under the discussion, and hopefully this will be implemented in the early next year. So this is source code structure. So we managed in the GitHub repository, so that we can you may find in the documentation. So as I told you that we have been starting with adding support of the new quantum resources in our QRMI library. So this is a very brief step of how to develop and how to add new QRMI implementation to our stack. So first, how the user vendor need to define how user can enable your quantum resources, so that as a Qiskit primitive program or a custom SDK API. So also decide the resource name and implement the API client. Maybe I think that most of the quantum vendor uses the REST API, so that they will refer our implementation to implement quickly. Also, the quantum resource payload definition, if they need to specify other types of the payload to describe the quantum circuit, so that they need to update the payload definition and payload code. And then add the client library to allow the user to invoke their QRMI from their code. Yeah, this is almost done. So in this year, so in addition to the providing software itself, so that we have been supporting our HPC partner experience for the scientific output. This is one of the examples. So the STFC team has been using our software stack and run their experiment and publish their paper regarding the chemical simulations. So this is a great example. So this is the next step slide. So we will continue to work with the HPC community and partners to hear the feedback to prioritize the items and identify the missing functionality. So maybe we will focusing on the accounting information support as soon as possible. Also, we will prioritize the enabling new device support in QRMI. Also, some data center want to evaluate our software stack. So we need to start to deploy to the new data centers. Yep, this is the last slide. So as I told you that our implementation is fully open sources. So please visit to our GitHub repository and please play and try. So we just started our activity in this April, so that we have a lot of things to do in the next year. So that if you have any request or if you are interested in our activity, so that please contact me. So that please jump into our community call. Yeah, thank you very much for your listening.
Thank you, Otani-san. Yes. Yes, I think, you have many questions or comments on our activity. So please, give your, or question or thoughts, if you have. So, Peter raised his hand. Peter, could you talk?
Hi there, you can hear me, right?
Yeah.
Yep.
Yeah, so first of all, thanks very much for the nice talk. So I had a quick question about how resource allocation works. So presumably, if you're allocating, let's say, a quantum resource, there's always some classical node or some classical portion that goes along with it. So one question is whether that's actually the case, and then the second question is how does the allocation work for larger algorithms where, let's say, you require large classical and quantum resources, and maybe they have to be interleaved. So maybe you do a large classical computation, then a large quantum. Like, would both quantum and classical resources be blocked? Would one be released for the portion where it's not being used? How does all that work currently?
Yeah, I think that it must be depending on how to organize the Slurm job for that HPC workload. So that if we have, for example, the large effort of the classical workload as a pre-process or post-process, so that it seems that one solution is that splitting those workload into multiple Slurm job. So that in this case, so the pre-process uses the CPU, and other pre-process must be for the QPU. This is another thing, another job. And lastly, if you have any processing with the GPU, so that I think that it would be better to create a separate job. And we can organize those three steps, multiple jobs, by utilizing the Slurm job array. So that if we can do that, so that we can minimize the latency and unnecessary resource locking for the QPU, CPU, and GPU.
So basically, the Slurm, allocate the classical, HPC resources as well as, quantum resources. That's the design, right, Otani-san?
Yeah.
Got it. Thank you.
Okay, next one. Could you? Yeah.
I'll go. That's I'm next.
Yes. Shihata? Okay,
Yeah,
I mean, okay.
I'm here. Yeah.
Okay.
I have a couple of questions. So I'll start, I guess, it's a continuation of Peter's question. So if you have an MPI program and you want to have both classical and quantum running at the same time, and you want to be able to offload the quantum from the classical directly. I think Recon did that with the SKQD algorithm where they overlapped both the classical and the quantum. Were they using QRMI or did they have their own implementation? And I'm just wondering if it supports that usage model.
We've not tried to test such use cases, but our QRMI, just like the same API library to access the quantum workload, so that if we can establish such kind of the scenario by using the SLAM user interfaces so that we can deliver, we can achieve such kind of the scenario with our implementation. Sorry, I can say this is what I can say for now.
Sounds good. The other question I have is, can we go back to the QRMI? You had a box with the QRMI and the components in the box.
This one?
Yeah. So
Okay.
is the QRMI, is it a library or is it just an API definition that then people can go and implement themselves? I was a little bit confused on that.
Yeah, so that I have been receiving a similar comment from the community. So QRMI is the definition of the interfaces. And also the QRMI, we call the QRMI vendor library, is the physical file to provide the interfaces. That is a dynamic shared library.
Okay, so it's not mandatory to have the physical, like somebody can go and implement their own shared library for QRMI and use that. They don't
Right.
have to use the, okay.
Yeah, currently, so the this is one of the things to be implemented in the next year. So the currently all of the vendor implementation need to put to our GitHub repository and the single library. QRMI library is a single binary. But I know that some quantum vendor want to manage their code in their GitHub repository. So that we are thinking of providing the pluggable interfaces to add and remove the QRMI library from the main QRMI library in the future. So this is one of the things to be implemented in the next year.
Sounds good, thank you.
Yep.
Next, maybe Laura.
Hi, this is actually Martin. Laura and I are sharing a channel here.
Yeah.
Sorry about any confusion here. I just was curious, how much is this actually tied to Slurm? Can other resource manager be swapped in, and if so, how much work would that be?
Yeah, so we've not yet evaluate the other workload management systems. But as you can see from our GitHub repository, our Spank plugin that interact with the SLAM and QRMI is very thin C program. It just retrieve the data from the SLAM cluster and set the environment variable. So that if the other workload management system can provide the similar functionality, so that we can easily enable to support the other workload management system. So that, for example, that in the supercomputing 25, so the IBM has demonstrated the IBM LSF as a workload management system with our QRMI to invoke the quantum workload. So this means that we can easily port our implementation to other mechanisms if some small dependency is resolved by the workload manager.
So in my understanding, the QRMI is very general implementation, and there is SLAM specific implementation. So
yeah, very small.
Yeah, I'm asking because we're considering switching, at least for some other concepts, into Flux and a more dynamic hierarchical resource management scheme.
Or this has not yet being discussed in the community, but for IBM, so that we are going to consider to support the Flux as a workload manager in addition to the LSF. But this plan has not yet been finalized. So that, yeah, we are going to consider more.
Okay, thanks.
Yes. Next one, Thomas.
Yeah, this one sort of covered that last discussion, covered mine. But I was just going to ask if there were Slurm version dependencies or upstreaming. I guess would be the side of this to make it into Slurm's standard set of plugins.
Yes. Yeah. So the Slurm compatibility. Slurm provided a versioning of the modules to be loaded by the Slurm daemon. So if we change the Slurm version, so that we need to rebuild only our Spank plugin to fit to work with the Slurm version. So that by looking at the recent SketMD activity, so currently there was no interface changes in the Spank plugin interfaces. So this means that currently we don't have any impact from the Slurm version upgrade. But as you may know that Slurm was acquired by the NVIDIA this morning. So versioning and maintenance policy, I'm not sure what happened in the maintenance policy of the Slurm by the SketMD. Sorry, this is my answer.
Thank you.
Mew?
Yeah, hi. So a question, if we'll go back to the workflow diagram that you guys had, the Slurm workflow diagram, that big one, yeah. The Slurm here, in a typical deployment, like if you're deploying on, I can't remember the name in the New York, for example, where's that Slurm D running? Is it on a, like the HPC center administrator assigns like a classical compute that is coupled with the quantum computer, and the Slurm daemon runs on the classical compute, and all this process runs on that node?
Yeah, so the Slurm daemon is running on the each computational node to allocate the resources, which is responsible to allocate the resources and to fork the executable as a HPC workload and shut down the job execution. So I answered that Slurm D is deployed on all of the computational node in the Slurm cluster.
Right, and I guess my question is the quantum computer, well, the quantum computer is a computational node, but so what does that look like? Because the quantum computer has some classical component. Who manages the classical component in this diagram? Is it the HPC center that sort of says, okay, this node is coupled with the quantum computer, and then here is your quantum resource per se?
Yeah, you are right. So currently from the Slurm cluster, so the quantum resources are populated as a CPU classical resources. So in some users case, so for example, the RPI data center uses the partitioning to specify which node can accept the quantum resource request to run. So this is one of the case. So another thing is that the HPC administrator want to control and monitor the usage of the quantum resources so they can utilize the Slurm ticket mechanism it's like a semaphore of the in the software world. So yeah, this is my answer, so that we can choose which node can be handled the quantum resources by utilizing the SLAM functionality and the configuration.
Makes sense. Thank you.
Yeah.
Sorry.
Yep.
Is there any other comment? Okay, Laura or Martin? Oh, could you unmute?
Yeah, sorry, we had problems with the unmute button, which was covered for a moment. I had a quick question on the selection of the quantum device. If I see this right here and also in the example, you have the quantum device specified as a parameter to Slurm, right? So as part of the Slurm batch job. Does this mean that you have fixed to this one device, or is there an ability to dynamically also select devices at runtime at the job? So if you want to have, for example, switch between a neutral atom system and a superconducting system based on the circuit you have, or you want to pick your right device, do you have to decide this when you submit the job, or is there a way to delay this decision?
Yeah, so in our current implementation, so the -QPU option accept the multiple resource name in the list. So for example, the IBM phase and Fresnel for the Pascal cloud. And our infrastructure code try to reserve those resources. And once those resources are available, so the later thing is that up to HPC users program, so that they can find the allocated resources from the program, so that they can choose which resources they want to use and run their quantum circuit against the allocated resources. This is our implementation, but in the future, maybe in early next year, so that we can improve this quantum backend specification. For example, the HPC community users want to allocate the HPC resources by specifying the IBM backend with more than 127 qubit, instead of specifying each concrete name of the resources. So that we are going to implement such kind of enhancement in our Spark plugin in the future. Did I answer to your question?
Yeah, that makes sense. But to the first part is, so if I specify multiple resources, you would allocate and reserve them all, right? Is that correct? It's a superset of getting. Okay.
Yeah,
Thank
basically, this kind of discussion should be based on the use cases. So as you know, currently, or one, most of HPC center has several, few, QPUs. In that case, this kind of, or specification is enough for the current use cases. But in the future, maybe there are several options to specify the QPU. Like now, we maybe need to support some partitioning mechanism in the large logical QPU system. Then in that case, we need to think about how to query the required QPUs for each program. So maybe this is a kind of or big or point for this future discussion. Whether or based on the evolution of the quantum resources, hardware side, as well as the application, or requirement. So maybe this is another point to ask people to join the discussion in our open or call of this QRMI. Thank you.